Hello, today I'd like to investigate a cool floating point example and see what we can learn. Do you remember the quadratic polynomial where you have three coefficients listed in ascending order as A0, A1, and A2? And I gave a numerical example for this, and that's where the A0 was 1, A1 was -4, and A2 was 3. For that example, we know that the two roots, x1 and x2, are 1/3 and 1 respectively. Those are the values that make the polynomial vanish. So we want to see how our simple floating point system works with this. So remember the two-digit floating point example from the Matlab book. We are going to have a sign S1 multiplied by a two-digit significand D1.D2, and then it's a base 10 system, a decimal system, so we're going to have a base 10 raised to the exponent S0 times D0, and D0 is a digit that can range from -9 to +9, and we're going to claim that it's a rounding system. All right, and the FL of x, what that means is that floats the value of x. So for example, if your real number is 104 and you float it, since you only have the two digits, that's going to round down and just show up as 1.0 times 10 to the 2. The 105 example is going to round up to 1.1 times 10 to the 2. The machine epsilon for this example is 0.05. In the rounding, the relative error of the rounding, I'll call rho sub x, and ordinarily you show it as an absolute value, so it would be the floating point result minus the true value divided by the true value. I like to free it up for discussion purposes in investigating errors. So free it up means that you sort of remove the absolute value and then you rewrite it in this way, and so basically you multiply it through by x and then regrouping. So this is another representation of the floating point value of x, and relating it to the original true value x and then whatever the error is, and that error is going to be less than the machine precision. And then I give an example here to show that, yeah, the relative error, it almost gets as high as the machine precision. So that x that's coming in, that's a real number. That's a real number, and there's an infinite number of real numbers, but there's only a finite number. The result's going to be a floated value in our set F. So there's only a finite number, so obviously you're going to have loss of resolution, especially in this case we only have the two digits. For multiplication and addition, and I show an example here, you end up with kind of the same thing. You're going to have a relative error. I show it here as rho sub plus, and what comes in here, your x and your y that you're adding together, those are floats, but the sum of those floats is a real, and it just falls back to the previous thing, that you're taking the real thing and then you're going to float it, and the result is going to be a float. So it's almost the same thing. And multiplication wise, it's also the same thing. You're going to multiply two floats, but their result is going to be a real that you float back, and that's how it is. So these operations, the float operation I showed you, the addition operation or the multiplication operation, those operations I'll just generically show as rho sub 1, rho sub 2, etc. for their to describe their relative errors, where each of those relative errors are less than or equal to the machine precision. So getting back to our polynomial, do you guys remember the Horner sequence that I showed you? So the Horner sequence says you start, you initialize, with the highest coefficient, and the sequence basically says take what you had before, multiply by x, and add the next coefficient. So that's the first step after you initialize. Then you take that result, multiply by x, and add the next coefficient, the previous coefficient. You actually were able to implement the Horner sequence for a quadratic polynomial in 4 steps. You take the first product, a2 times x, and I'm going to call row 1 the relative error for that floating point product. And then you add to it a1, so that's going to be a sum, so I'll call that row 2 for the relative error for that. And then you multiply that result by x, and I'm going to call row 3 the relative error for that product. And then the last thing is you add in that constant term, so I'm going to call row 4 the relative error for that final sum. Each of those coefficients, even in our example, the coefficients are floating point values. We're going to try some different x's, though, that are floating point values. So think of everything coming in as floats. Okay. So there, the a2x, that is the first floating point operation for row 1. And then you take that result and add to it a1, so that's your second floating point operation. The third floating point operation is where you multiply by x, and you would pick up that 1 plus row 3. And then the final one is where you add in the a0, and that's where you pick up the row 4. So this is the floating point result of the polynomial having floating point coefficients evaluated at some floating point x, and it's evaluated using the Horner sequence that I just described. So this representation is equivalent to the error representation, and we want to do that so we can find out what the bounds are. So I take what I had before, and I'm just trying to rearrange it. I want to try to find the true value of the polynomial. So I rearrange it, so I'm trying to collect things that go term by term. So there's the a0, it's only going to get the row 4. A1x is going to get the effects of row 2, row 3, row 4, second, third, and fourth operation. But that highest term is going to see the effects of all 4 operations. And then if I just keep going here, I'm trying to take what I had before and multiply out the factors here, and ignore the crosswise higher order terms like a row 2, row 3. I'll ignore that because rows are really small and their products are going to be really small. So I ignore those higher order terms and rewrite it as an approximation. So the floating point result of the polynomial is approximately equal to, that would be the true value. And for the a0, I'm only going to get a row 4. For a1 x, I'm only going to see the row 2, row 3, row 4 linear terms. And then for my a2 x squared, I'm going to only see those 4 row 1, row 2, row 3, row 4 linear terms. And then here, I'm almost to where I want to be here. Almost to where I want to be. I take the true value and bring it back over with the calculated floating point Horner sequence, and then I do the absolute value there. And I know that's going to be less than or equal to the a0, so I'm going to be absolute valuing the terms over here, a0, and then here for the a1x term, I'm going to end up with a 3, factoring out the machine epsilon, because I know that each row is less than a machine epsilon, and I've got 3 rows there, so I have a 3 scaling the a1x, and then scaling the a2x squared, I'm going to have 4, because I have 4 rows there. So there is my bound right there. So I know that the calculation of the floating point value and the true value, the difference between those, the absolute value, is going to be less than. This is always true, no matter whether x is a root or not. Now, here's a big deal. What if the true value could be 0? If that's true, then set that equal to 0, and then you're looking at, well, does the Horner sequence, the absolute value of the Horner sequence, is that less than all of this, which I call error bound or max error? If it's less than that, then you know what? It's a root. And I kind of also rewrite it this way, take away the absolute value, say, well, the floating point value of the polynomial is between minus error and plus error. I'm going to call it a root. So you calculate the floating point value, again, using the Horner sequence. And you know what? You actually calculate this error bound using sort of a modified Horner sequence. You're using absolute values of the coefficients. You're using absolute values of the proposed x root. And then you have to scale the coefficient, each term, by an appropriate, effectively an integer. Take the whole thing and multiply by machine precision. So I call it just a modified Horner, and that's how it's implemented. So this would say, if this is true, then that proposed x is a root to within round-off error. I think it's pretty fascinating once you can wrap your head around that, how powerful that is. So I implemented some code in Matlab where I'm given a real value x, and I output actually a structure where I have a sign, I've got a significand, a 2-digit significand, and I've got an exponent. So this is the code that kind of takes an x and breaks it apart. So in my system here, something that's been floated is actually a structure of 3 elements: a sign, a significand, and for the 2-digit example, it's where the x divided by 10 to the exponent is rounded to 1 decimal place, 1 point after the decimal. So that's what I have. And then I do some special cases if it's effectively 0 or too big. So that's our float2 function. And then the float2u just takes that structure and just unravels it and returns a float. And then I've got an add that takes two structures, 2 floating point values, AF and BF, and unravels them, adds them, and then floats it back and returns a structure. The multiply does a similar thing. It unravels 2 given structures, multiplies them together as reals, and then floats it back. Now I go and take a look at a script 2. So my script 2, in the script here, a suffix of a D means that's a double, and the suffix of an S would be a structure representation, a floated structure representation. So I've got my coefficients kind of configured here, and then what I do is I look at some proposed roots. I'm going to look first of all between 0 and 1, and I'm going to do that with 2 decimal precision in my first iteration through here. So here's my first floating point multiplication where I'm taking A2, multiplying it by x, and then I add in the A1, multiply again by x, and then I add in the A0. So there's the 4 floating point operations that effectively do the Horner sequence. So that last result, which I called as sum of the 4th operation as a structure, that is my polynomial evaluated at x in the Horner sequence. And then I do the max error. So this max error here is that bit that looked like this. So I've got the absolute value of the coefficients. I've got 3 on the A1, I've got 4 on the A2, and I'm taking all of that and multiplying by the machine precision. And then what I do is I'm collecting x values, and I'm collecting the y values as the unfloated result of the polynomial. Now this last one here, my z, that's going to be a Boolean, and what that's saying is that the unfloated polynomial value is between minus error and plus error. So that's what that's saying, and then I print it out. And then I repeat it at a little bit different granularity for values between 1 and it looks like 2. A little bit different granularity to keep the 2-digit sort of representation. Print that out, and then I plot my polynomial value, and I also plot the Boolean value. So that's kind of how the script works. So now when I go and run my script 2 it's called, see what I get. Okay, so it's plotted out. In blue, that's the polynomial value, and remember we were looking at a root at around 1/3, and we're looking at a root around 1. Well, you know, 1 can be represented in our system, but 1/3 actually can't. We have to show it as 0.33. The Boolean is actually showing a swath of points that look like potential roots. That's what the floating point's telling you. You can see here with the jaggedness, it's not the resolution for the floating point system is not that great. But let's go look at the raw data, and it's just the printouts from my script. And if you kind of look at it, here are the x values, and around about 1, you know, we're kind of expecting the floating point value of the polynomial to be about 0, and it is. But all through here, if you look at what the Boolean is looking like, all through here, the floating point value is between minus error and plus error. And if you look at it, there's some changing of the signs here actually too. So we're kind of hovering around 0 right near 1 and actually changing signs, so it's difficult to say what's there. But again, to within round off error, all of these could be thought of as a root. I'm going to go back to 0.33. So 1/3 right in here, we know that 0.333 or 1/3 is a root. You can't really represent that in this system. But right in here, there's a whole bunch of points that actually show up as 0. These are all showing as root. And where the root turns on is back here at about 0.24 for x, because that shows the polynomial is, the value is 0.21, and that is between minus 0.23 and plus 0.23. So right in there is where it turns on, and it doesn't turn off again until about 1.6. Go back and look at that. Yeah, so what the system just doesn't have enough resolution to really discriminate between the 1/3 root and the 1 root, and it kind of treats it as though it was a double root. That's what it's looking like. So the 2-digit example here is given that whole swath that looks like potential roots, and we know it's a quadratic here, so we're kind of looking for 2 roots, and using this system, it starts to look like it's a double root because everything's kind of close to 0 in this area. So what would you do? Oh, let's go take a look at adding a decimal place to our example, and that's what I did. Is, I took what I had before with the 2-digit, and I've added an extra digit here on the significand, so I'm going with 3 digits. Okay, so when I do the float now, the 104 is going to be 1.04 times 10 to the 2, and the 105 is going to be 1.05 times 10 to the 2. I get better precision, so my machine epsilon now is 0.005. It went from 0.05 to now 0.005. So I'm set up for success here with a 3-digit system. And if I were to go look at that, clear workspace, yeah, so float 3. So float 3 is a similar function. It's going to be a 3-digit one where I pick up another digit on my significand. And how I do that is just with the round function. Instead of 1 here, I have 2. So that's rounding to 2 decimal places after the period. So we're all set up there. And when I go look at running that, so float, let's say float 3 of, let's do 1/3, because we know that's a root. So float 3 is going to look like 3.33 times 10 to the minus 1. That's correct. Compare that with the float 2 of our proposed root. So that's 3.3. So you can see you've got better resolution. And what I did is I rewrote script 2 as script 3, and I had to really change the resolution of going from 0 to 1 because I need to have more points in that example, and then from 1 to 2 also same kind of thing. So I'm going to end up with a lot more points. My max error, I updated the machine epsilon for that. So I'm basically set up for success here. Everything's a float 3 op now. And then when I go run my script 3, oh, looky here. We're going to get a nice smooth polynomial function because we have the higher resolution, and that's the floating point representation. And then look at what's happening with the roots. So our Boolean roots, we do now have definitive areas where we have our 1/3 that we can focus in on. And we also have our 1 where we can focus in on. If you go back and look at the data, is root, coming back get to about 1. So for 1, looks like that area starts at about 0.93 or 94. That's where our calculation of our Horner sequence is between minus error and plus error. And you can see that the Horner sequence is negative, 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 negative. And then it comes right in here, right about 1, and it's starting to change signs. A couple of times it flips signs, and of course at 1 we have 0. And then we kind of keep going. Around 1.06 it turns off, being a root. So the 1 is captured as a root, really highlights that. And I'm going all the way back. So you can see here I've got my x with a lot of resolution when I'm less than 1. Not a root. Not a root. So I'm getting back to the 0.333 area. And where's my root turn on? Yeah, so I see it turning on now. So it turns on at about 0.318. And then you can see it's plus, 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 plus. And then right about here is where it changes sign. So somewhere in here there's a root. And we know it to be at 1/3. But it's actually not showing up there. It's actually showing a little bit later. And it's flattening out in this area for that resolution. But it's looking much better with the 3 digits than the 2-digit. So the 3-digit example is much better as we thought it would be. And the reason it's much better is because we have now separated the roots. And with the roots properly separated, you can go in with a polish technique and get a good root to report something very close to 1 and something very close to 1/3. So key points here. Finding roots here, we actually knew the roots a priori. We knew that the roots were 1/3 and 1. So you might kind of dismiss what I've shown you and think it's trivial, but in actual practice, you don't know the roots beforehand. So you have to go off of your numerical analysis to declare what the roots are. So this technique that I've shown you is really important and applies to even double floating point type of applications. And even in the double floating point with double floating point precision, the effects I've shown you where roots sort of coalesce from a numerical perspective, that happens, and it's really daunting to kind of navigate that. So anyway, just very important stuff I've shown you here. I hope you enjoy.